We're going live. The creepy screen is back up. Good afternoon, campers. How's it going? So I have my own channel now for our class on the YouTube. And I have 4 videos posted so far, the oldest of which already has 21 views. And I'm not even thinking it's you guys. So how cool is that? Don't worry, none of your voices are probably picked up on my microphone, so you don't have to worry about that, right? Aaron? Yeah. That's good. Yeah, that means I have to try to remember to rephrase questions when they get asked of me. Okay, we'll say goodbye to Lisa's email and to-do list, and we'll pull up Blackboard. So once you go back into your quiz, you'll be able to see what I think the answer is. My plan is, as I said, everybody gets full credit, but I'm going to read your answers and get a sense of what people are saying, and also if you have questions or things in there, I may respond with individual feedback. So first question, all the terms that you can think of that go with the phrase level 2. Shout them out. Between, I'll take that. What else? Time invariant, I will take that, although I don't think I wrote that one down. Good one. I'll take that also. Someone's been reading the book. I won't take that one because fixed effects can be at any level. They're expressed at level 2 in terms of like a hierarchical equation, but they're not technically level specific. I mean, they're not level 2 specific. So individual, interpersonal, any of those works? Random, yes, random effects. So random effects is a umbrella term that we're going to have random intercept and random slope as specific types of random effects, but those are between person sources of variation. They are indicated by what letter? U. Yes, tau square for the variance. I will also take that. Tau square sub U0 is random intercept variance in the notation. Any others? Cross-sectional, if you're talking about intercept variance, you can also say that. Mean differences, I would take that also, because that's what random intercept variance means. Any others? Okay, so let's do level 1. Everything else, right? Intra, there's one. Within person. Time varying. Longitudinal. What letter? E. What's the word that goes with E? What's it called? It's not random. It's going to be the other R word. Residual, yes. And I am going to be consistent in those names. Some textbooks talk about level 1 residuals and level 2 residuals, and I think that's just mean when you're trying to get your feet underneath you, so I'm going to stay consistent. Level 2 sources of variance are going to be random things, random intercepts, random slopes. Level 1 sources of variance are going to be residual. And that's what the meaning of the E is. It's within person, over time, longitudinal, all of those things. Any others? Intra, that's the other one we said, right? Intra. Okay. Questions on any of that? All right. Third question. What's a random intercept for? What's it do? What's it predict? Well, you wrote something, right? So it's not like this is a pop quiz in the sense that you didn't just spend 15 minutes answering these questions, right? I'm going to wonder. I'm going to be like a game show host. I wish I had a microphone to stick underneath each of you. Egan, I'm going to stop with you. What's a random intercept for? Can I answer it later? Sure. I'm feeling generous today. Lucas, what's a random intercept for?
That's a type of mean. Helps us compare between groups versus within groups.
It characterizes between group variance. I'll give you that. It characterizes mean differences that are between persons. Can someone answer my question with the word pile in the sentence? Or variance component? I heard someone. You? 2 piles, yes. Yes, so we have all together 1 pile. Once we put in a random intercept, then we have 2 piles. The pile that it belongs to the random intercept characterizes person mean differences. What does it do instead in terms of predicting covariance across time? Does it predict some? Yeah, it does. It says that occasions are related because of constant mean differences. So it predicts constant covariance across time. Also related to this, if I were to make an effect size that describes how much of my variation is due to between person mean differences in the intercept, what would that thing be called? Starts with an I. ICC, which stands for Intraclass Correlation. Yes, indeed. Good. Anybody write anything else that they're not sure if it's right or not? Remember, I love wrong answers. Wrong answers are really helpful in diagnosing misconceptions. So if you got a wrong answer, be proud.
Use the ICC to figure out how longitudinal versus cross-sectional it is.
So if it is more cross-sectional, is the ICC bigger or smaller?
More cross-sectional is bigger.
More cross-sectional is bigger. And what is a bad ICC if you're going to be the first student in your area to do a longitudinal study? Yeah, 1. That is very bad news. That means game over. Does 0 ICC mean game over? Nope. Because even if it's 0 in an empty model, it's not going to stay 0 once you explain the residual variance. It's going to come right back up. So there is no bad ICC except for 1. 1 is bad. 3 kinds of ANOVAs. Last question. So we're talking about between groups, 2 kinds of repeated measures, univariate and multivariate. What do they have in common? When people say the word ANOVA, what kind of estimation are they typically referring to? Yes, ordinary least squares to be specific. Now, is that good or bad? You need all the data. That's where it can be a problem if you have incomplete data.
They use listwise deletion.
It uses listwise deletion, ordinary least squares does. It also requires balance time. You can't have people have uneven time schedules in least squares, yes?
Can you also say about their assumptions about their error?
That's how they differ. So the 3 kinds of ANOVAs are all estimated by least squares. They all use what's called a saturated means model, meaning time is treated as a categorical predictor. Everybody has to have the same set of possible time values, balanced data. The way they differ is in their model for the variance. So what kind of relationship across time does a between groups ANOVA predict? I'll give you 3 choices. Whatever it wants, constant, or none. It's the between is the none. The none, the type equals VC. How about the univariate approach to repeated measures? Constant or whatever it wants? Constant. That's the random intercept model. That means the multivariate approach, whatever it wants. The term for that is unstructured. Yes. All variances and covariances are estimated separately. Indeed. So let me return then, picking up on that idea, to go back over the handout I cruised through very quickly at the end of last time, example 3b. This is from chapter 3, the second section. So this is data that you will get to know very well. As an example, the story is I have 6 sessions. These are older adults measured over a 2-week period. This is a response time task measuring processing speed. So even though this is an older adult sample, I'm not interested in aging per se. They're not getting much older over a 2-week period. What the background is to this is it's a study designed to look at practice effects in speeded tasks. There is a controversy in the field of cognitive aging. Whenever you measure cognition repeatedly, you have to give them the same measure over time in order to measure change. However, what happens if you do the same thing over and over and over again? You get better at it. Some people would call that like cognitive training, for instance. Some people would call that a practice effect and a nuisance. The problem is that if they're older, each time they do it again, you can't differentiate what is aging and practice. So this study was conducted in a short time frame just to get a sense of how practice effects functions in a sample of older adults, whether they were common or unique across tasks, and whether or not there were individual differences in what those predictors were. So this is a balanced data set. It is real data. It has 6 sessions, as I said. So 6 outcomes over time, 101 people, and the outcome is response time. So faster means a lower outcome. So these are 3 types of Anova models for these 6 response time scores. So it's the mean response time across trials for each session. All of these Anova models, the model for the means can be described with this equation. It looks like on mine, my little hat got turned into a box, but that should be predicted response time. So this is a way to write a saturated means model that corresponds with how the model is going to be parameterized in SAS. Parameterized meaning that's a $5 word that means set up or specified. In SAS, when you use the class statement to identify a categorical predictor, the highest numerically or the last alphabetically is the reference. That's why this equation doesn't have a T6 in it. These T1 through T5 are dummy codes that indicate all possible differences across the sessions, the times, relative to session 6 as the intercept. So beta 0 would be the expected response time at session 6. Beta 1 is 1 versus 6, 2 is 2 versus 6, and so on. So all 3 of these Anova models have that as their mean structure. Saturated means 1 parameter per occasion. So 6 parameters in the model for the means. Now the question is, what kind of variance and covariance do these different models predict? Between person says none. What makes that happen in terms of SAS is this right here, type equals VC. Stands for variance components. In the rest of the code, note that I am putting session as my predictor variable. Session is also on the class statement. That means SAS is doing the dummy coding for me. That means SAS will also give me predicted means per session if I ask for it on this ls mean statement. And diff equals all, can you guess what that does? All the differences. 7 letters, right? Yeah, 7 letters and an equal sign. It's beautiful. Because I'm going to be comparing the fit of these models, we talked about that at the end of class, I am saving the fit statistics table as a SAS data set. I wrote a macro that does fit comparisons for you, -2 log likelihood comparisons. So that's what this ODS output does. It's saving a table called InfoCrit, which is what SAS calls the information criteria table, which is this one right here at the top of the next page. And I have named that data set Fit BP Anova. That's my name. So the R matrix, to review some terminology here, this is my model predicted pattern of variance and covariance across the 6 sessions. There's only one number in it. I had told SAS, you know what? I want to predict that all 6 sessions have exactly the same amount of variance and that the 6 sessions have no correlation within persons. That is what this between person Anova model is, otherwise known as E only, otherwise known as just a simple linear regression. One pile of variance. We talked about -2 log likelihood briefly last time. Do you know what the res in here stands for? -2 res log likelihood? Residual, or I'll take restricted also. This is your indicator that you have asked for your model to be estimated in restricted maximum likelihood instead of regular flavor. Where's Teresa? We're going to talk about that today. Right? She went Googling about REML, and I'm like, no, talk to me first. It'll be okay. But that's letting you know that you've asked for REML. So if you ever look at output and you're not sure what you asked for, that will help you figure it out. So here is my solution for fixed effects. Note that session 6 is the one that has a 0 in dots, indicating that it is the reference. So response time for this task on average at session 6 is 1,672 milliseconds. The response time at session 1 was 289 milliseconds higher than session 6, and the others give 2 versus 6, 3 versus 6, and so on. So each of these comparisons that are given to you by default here are univariate wald tests because they're testing one thing, one difference, each successive pairwise mean difference relative to session 6. If I want to put that all together and say, are there any differences across time, across the 6 sessions, that is our friend the multivariate wald test, a wild test. That makes it sound more fun than it is. It's a wald test, modified wald test because we're using degrees of freedom. That's my omnibus main effect of time, what you would get out of an analysis of variance. It's just a specific type of multivariate wald test. So we would look at that and say 5 degrees of freedom because there's 6 sessions. We always estimate a fixed intercept. That's why it's always -1. So we have a fixed intercept and 5 differences. So these are testing the 5 differences simultaneously. F times 5 equals chi-square. So those numbers are interchangeable. You can report whichever one you feel like. They give you identical p-values. So yes, we would say there are some mean differences across time. These are the LS means, and I omitted the table that has all possible mean differences because it was too long and uninteresting. So we know that model is probably wrong because how likely is it that 6 scores from the same person have nothing to do with each other? Not very likely. So then we'll be like, no, why would you do a between person ANOVA on repeated measures data? That's silly. Let's do repeated measures ANOVA instead. The univariate version. 2-letter difference to get that. CS stands for compound symmetry, yes. That's a $5 word if I ever heard one. So this name goes by a lot of names. This model, excuse me, goes by a lot of names. I would call this compound symmetry. I would call this univariate repeated measures ANOVA. I would call this random intercept. I would call this a 2-pile model. We have taken what was 1 pile and split it into 2. How much of it is between persons mean differences and how much of it is residual variation around those person means. The code is otherwise identical, although I am saving the fit statistics from this model under a new name so that I can add those to my list here. R and R core, let me try and make this big here. The top matrix is the variance covariance matrix. So on the diagonal are the variances at each session. Sorted in the order of the data, so it's 1 through 6. Now, if you look at the number on the diagonal, is it the same or different? Same. Coincidence? No, that's what we told it to be. That's what compound symmetry means, same variance across time. How about the number on the off diagonal? Same or different? Same, yeah, and I use singular, so there's your clue, right? The number on the off diagonal. That's not a coincidence either. That's what we told it when we said compound symmetry. We said, yes, there should be covariance across the occasions from the same person, but it should be the same covariance no matter which pairs of occasions we're talking about. If I take that off-diagonal covariance and I convert it into a correlation, I get that same number in the R-core matrix instead. That correlation has a special name. What is it? Okay, I figured this would happen and I came prepared. So, brief story. Last Friday I turned 40. I know, right? I'm old and stuff. And I went up to Omaha to see my family, and my nieces made me a present. They said that they hope that being 40 rocks, and they gave me Pop Rocks. I let them have part of my present because it turns out they love Pop Rocks. Me, I have crowns and fillings, and I'm pretty sure my teeth can't handle this. Does anybody here like Pop Rocks? Don't be shy. In the years that you've had them, would you be willing to tell me, in exchange for a bag of Pop Rocks, what the special name of this correlation is? It starts with an I. We talked about it like 15 minutes ago. Hey, Interclass, would you? I also have suckers, because they hope that being 40 doesn't suck either. Would you like a sucker? Really? No one wants candy. I start throwing candy. Okay, I'm throwing candy for answers. Okay, so this is a correlation, 0.86. That's the intraclass correlation. Is that the proportion between or within? Oh, I don't throw candy for wrong answers. Between or within? Between. Aaron, would you like a sucker? What color do you like? This one's fine. Okay, ready? Well done. All right. Scott, do you want Pop Rocks? You're the only one who said. You don't. You want?
I said between also before she did that.
Well, that you're bad, right? You know what? Just since I missed you, you get all three. There. Oh yeah. Does anyone have kids at home that like suckers? No? Oh, okay. No. I've got more. Got more where that came from. Apparently I need to bring something better like booze or money. Maybe I should get like those little airplane bottles of liquor and start chucking those. Then I get some class participation. I might also get a visit from campus security, but if we're allowed to have guns in here, I should be able to throw liquor bottles at you, don't you think? If we're going to talk about the relative damage of one of those pieces of contraband versus the other, even if I hit you in the head with it, I'm not going to do that much damage. Yes. So yes, compound symmetry. Equal variance over time, equal covariance over time. The only kind of data in which this will work, meaning it will match the real data, is if you have a picture that looks like this or this. The common denominator here, parallel lines, constant growth across people. Everybody changes the same. That's the only situation in which you get equal variance and equal covariance over time, because this picture, each of these, allows for intercept differences. That's it. So this model is fine if that's what your data have. Odds are good though, particularly with 6 occasion data, that this is not going to be sufficient. So in learning how to read this output, all you really need to ask for is this table right here, covariance parameter estimates. That one comes by default. That tells you how many parameters are in the model for the variance. 2 piles. A CS pile, which is your random intercept variance, and a residual pile, which is your E variance. Level 2, level 1. The rest of the R matrices and R core matrices show you how these 2 piles then make a prediction about what your data is supposed to look like. If you add these 2 piles back together again, you get the diagonal here. The off diagonal is just the level 2 random intercept part, because it says the only reason that you have covariance between occasions from the same person is because some people start out higher, and that's it. Likewise, in counting parameters, all of the rows in your solution for fixed effects table that have numbers in them, that's how many parameters you have in the model for the means. So I'm trying to help you with future homeworks when I ask how many parameters in models. If you don't know, you can always just count. Every number that's listed here in blue in the covariance parameter estimates is a model for the variance parameter. All of the numbers that are listed here in this estimate column in the solution for fixed effects are parameters in the model for the means. So if I contrast the F value that I got from our all of the occasions are uncorrelated value, that's a 4.7. By allowing a correlation across persons, by allowing a random intercept variance, by allowing 2 piles instead of 1, my F jumped up to 32. Huh. Well, I think I like 32 better than 4. How about you? They're both significant, but it's like more significant. Why? That's the question of the day. Why? F ratio, broadly construed, ratio of what you know to what you don't know. Don't know, meaning unexplained variance, right? In this 2-pile model, the only type of unexplained variance that's going into that denominator is E variance. Well, you've separated out the variance that's relevant for testing whether or not session differences happen from the variance that's irrelevant. So if I want to know if session 2 is different than session 3, whether or not people start out differently is irrelevant to that test. And in this case, people starting out differently, random intercept variance, was 86% of the data. So yeah, if you get rid of 86% of what is unexplained because it's in a different partition because it's irrelevant, things look better. Now, is that too good? Do you think that people changing all the same parallel change is likely in this case? Does everybody improve at the same rate? Probably not, no. Pry, by the way, means probably in my Midwestern vocabulary, in case you haven't heard me say that before. I will also accept probably and probably as substitutes, but probably not. So then we have a third choice. The multivariate approach to repeated measures ANOVA, or Manova as it might also be called, type equals UN. What does that mean? Unstructured. The pattern is the data. Everything gets to be what it wants. Here is the pattern. This is the right answer. I will just tell you that. This is as good as it gets with respect to predicting the means, variances, and covariances across sessions, because every single one of them gets to be a different number. Saturated means, unstructured variance, This thing is called the H1 model in structural equation modeling land. So if you look at the numbers on the diagonal, again, these represent variances at each occasion. Do they look the same or different to you? Different, huh? Like different randomly or different in a pattern? They get smaller, yeah. Do you know what kind of picture would cause that? Since I'm drawing it down because these are changes in response time across time, people get faster. If people get faster at different rates, that causes the variance to shrink. Less variance at the end than at the beginning. Conversely, if people go up at different rates, the variance is smaller at the beginning than at the end. But different in a pattern. If you see this in your data, the right answer is almost always some kind of random time slope model. Now, whether it's linear or nonlinear or quadratic or what have you, that's left to be determined. But this pattern is a dead giveaway. Individual differences in change. The pattern of correlation is a little bit harder to pin down, but generally the occasions that are closer together in time, so the first off diagonal are occasions that are 1 unit apart, those correlations are a little higher than the correlations that are further apart in time. Also a dead giveaway. So this indicates that there are differences across time in covariance and variance. Are those differences significant, though? So what I'm asking is, does this two-pile model that only has random intercept variance and residual, is that not as good as letting everything be what it wants? That's an empirical question. So how many parameters different are these two types of repeated measures ANOVA? I'll give you the easy one. How many parameters for the model for the variance are in a two-pile model? Anyone? 2. Lucas, you get a sucker. Thank you. 2, yes. How many parameters are in this beast where everything gets to be what it wants? And feel free to read from the screen. For a blue one or butterscotch? Yes. Do the math for me.
42 divided by 21.
Hey, 21. Blue is my favorite flavor, broadly construed. That's an office reference. But have you ever noticed how many times like blue is a choice? Gatorade, liquor, suckers. Blue is my favorite flavor. But yeah, 21. So 2 versus 21 is the question. Is 2 good enough and is 21 too many? How we answer that question is by comparing the -2 log likelihood from those two models, 8353 versus 8929. My little macro program does that for you. So the way these macro programs work is that if you copy the program itself into your code, it will say macro and then a name and then a bunch of lines of code and then it says mend and then a name. You don't change anything in there. You then refer to the name and you tell it the information that you want to swap out to make it run. So for instance, I have a little macro called fit test, and it takes 2 pieces of information. The fit statistics table from the model that has fewer parameters and the one from the model that has more. So if I want to contrast a 1-pile model to a 2-pile model, That's right here. The difference in -2 log likelihood is 802. That difference needs to be bigger than 4 on 1 degree of freedom. So yeah, 800 is bigger than 4. I then compared my 2-pile model to my 21 parameter extravaganza, everything gets to be what it wants. And here's the result. So its significance, the p-value was so many zeros that it didn't even print, but what does it mean? Got suckers left. Fruit punch? Hawaiian punch, actually. Oh, that stuff was good. Multivariate is significantly better than univariate. Which one's significantly worse? Phrasing it the other way. Claire? Yes. Do you like orange? Butterscotch, yes. Properly motivated, students will answer questions. So yeah, you can look at it this way. 2 piles is not good enough. 21 parameters is better. Now, don't you wish there was something like in the middle there? That's like the difference between buying toilet paper at Sam's Club, where there's like 7,000 rolls in a package. You might not even get it in your car, versus buying them one at a time, right? Wouldn't it be nice if you could just get like 10 or 6? Yeah. See, that's what the rest of this course gives you, is things in the middle. Things that are possible once you switch over to likelihood estimation that are not possible in this world of Anova. So the Anova models that you've learned are special cases of a family of broader choices. That's the big picture there. One size fits most, as I would call them. Questions on that concept? All right, then we're switching back to lecture 3 again, because I have to talk about model comparisons and some of the nitty-gritty. A lot of these slides that are in here are sort of archival. I have simplified my approach over the years to make it more foolproof and less prone to being screwed up. Here is the big picture. We're staying in REML as much as humanly possible. Even though it says restricted, REML is not actually restricted. So this idea of comparing -2 log likelihood that we talked about last time, we can do that in ML or in REML equally well. What you can't do is do one model in ML and another model in REML and compare them. They have to be the same. So this is what we just did, more formally, a likelihood ratio test. The difference in -2 log likelihood as a function of the difference in parameters. When you add parameters, your model can get better or not better. When you remove, it can get worse or not worse. And information criteria for your next homework. I want to point out something very important here. The last bullet on here. The number of parameters that are relevant in computing information criteria in REML, it's only the variance ones. The number of parameters that are relevant in computing these information criteria in ML is all of them. Stata screws this up, by the way. It uses all of the parameters both of the time. So your output in Stata will look a little bit different. So what is the difference between regular flavor maximum likelihood, as I call it, and the REML flavor? I gotta get my stick out. Tell me, yeah, I've got it here. Phew. Do you remember this thing in like your intro stat class when people talked about population versus sample formulas? And the gist of it was population means you know everything you need to know, and sample means you had to estimate something to figure it out. So in the context of just estimating variance, like in an empty model, you have to estimate the mean first before you can estimate variance. So do you take that into account or not? If the answer is yes, you take that into account, your variance is actually more because the denominator is bigger. Is smaller, excuse me, is smaller. Variance is bigger because the denominator is smaller. If you don't take that into account, if you pretend like you have a population, then your variance is smaller because your denominator is bigger. You're used to seeing the top formula in the world of least squares, where denominator degrees of freedom always take into account the number of fixed effects you had to estimate. That's REML. And that's why I keep saying REML and least squares are the same thing if you have complete data. If you have incomplete data, REML doesn't require listwise deletion, and that's why it's better. This difference in what your variance is matters more when you have smaller samples at level 2, or your highest level of the model, number of people in this case. If you have less than 100 people, you probably should be using REML for everything. Once you get past 100, it matters less which you use. But we're going to stay in REML as much as we can because those variance components are unbiased. The problem is that REML is only available when you have normally distributed residuals. REML is not available for any other kind of distribution. REML is not available in the world of structural equation modeling, which is why some of you have never heard of REML before, because it's not a thing in M+, for instance. Regular flavor maximum likelihood is what is used in CFA, SEM, IRT models, and so that's the version that you may have seen before. Both of these are full information. So the number of parameters that are in the model is orthogonal to the choice of estimator. So Teresa, I'm trying to answer your question now. Try and keep all this stuff separate, right? Like if I have a saturated means unstructured variance model for 6 occasions, like I just fit, that's 6 parameters in the model for the means, 6 different means, 1 for each mean, and 21 variances and covariances. Okay, that's what it would be under ML or REML. The difference is that the variances would be smaller if ML gave them to me than REML. Where number of parameters matters is in AIC versus BIC. The number of parameters in REML disregards the 6 that are from the model for the means, and it would say there's only 21. That's where the rub is. The reason for that, why it disregards them, is because in order to do a valid model comparison in REML, you cannot change the model for the means. It has to be exactly the same. Otherwise, it's not valid. It's trying to maximize the likelihood of the residuals. We'll see more of the details of this computationally in a couple weeks. But because residuals are defined based on what the predictors are, they're not on the same scale if you have different predictors. So the only kind of model comparisons we will be doing using REML are when we're changing the model for the variance. So this is why we were using it just now in the Anova example. Let's see here, let me pull that back up for a second, make this point. The very first part of the handout said all of these 3 models have the exact same model for the means, a saturated means model. So they are equivalent in terms of their model for the means or their fixed effects. The way they differ is in the model for the variance. And that's why it's okay that we use REML to do likelihood ratio tests to compare the model for the variance. So what we will be doing, anytime you add a fixed effect to the model, fixed means what? Model for the means, everybody gets the same, yes. Anytime we add a fixed effect, like if we have a linear time slope versus a quadratic time slope, and we add it as a fixed effect, we're saying on average is their linear change, on average is their quadratic change. We're going to stare at the p-value. Wald test. I don't need any model comparisons for that. I can do a univariate wald test for each new fixed effect, and I can do a multivariate wald test for a set of fixed effects, such as a set of mean differences across a categorical variable. Where I need to pay attention to likelihood ratio tests is when I'm adding terms to the model for the variance. 2-pile versus everything gets to be what it wants is one case. Random intercept only versus a random intercept and a random time slope will be another case. 1-pile versus 2-pile, all of those things. When we're mucking about with the model for the variance, that's when we pull out the likelihood ratio test. And those likelihood ratio tests have to be conducted on the exact same model for the means to be valid. Let me, by the way, if you ever have questions about SAS code for proc mixed, linked on the course website up here is my SAS syntax guide that talks about how to get your data in, but then the rest of it is a very specific walkthrough of what all of the commands do in proc mixed. So I took this out of the manual and I tried to make it organized in English as much as possible. So if you're ever not sure like what a SAS command does, you can come here and get the nitty-gritty of it. In your homework, which you can now start doing, homework 3, there's no data for this. The computational part is asking you to calculate AIC and BIC. Now, you all know how to use a calculator. Most of you know how to make a spreadsheet too. That's not what this is about. The idea is for you to decompose the language to figure out how many parameters I'm talking about based on the names I'm using, and which kind of parameters are going to go into the calculation for AIC and BIC depending on ML versus REML. So I'll do the first one for you here. Each of you is going to be given a different -2 log likelihood. I have 5 occasions in this example. So if I'm saying, all right, saturated means for 5 occasions, how many parameters in the model for the means then? I have purple, orange, peach, another blue, and green. 5 occasions, saturated means. How many means is that? 5. What color? Okay, there you go. Yes. Unstructured variance for 5 occasions. How many variance and covariances is that? Yes, it's number of occasions times number of occasions plus 1 divided by 2. So 15. So I'm at 5 for the saturated means, 15 for the unstructured variance, and I'm in ML. ML counts both. So the total number of parameters then would be 20. Given a -2 log likelihood of that number, you can calculate what the AIC and BIC would be using 20 parameters. So I've got saturated means, empty means, unstructured variance, compound symmetry, and then these ones down here are for the alternative covariant structures starting in chapter 4. And then we have drop-down questions that are trying to generalize these concepts. I will tell you what to pay attention to in these. I'm asking you which of these is a valid likelihood ratio test. You need to keep in mind the rules for what can be compared when you're using ML versus REML. So in REML, the only kind of comparisons that are valid are variance model comparisons. The model for the means has to be the same. In ML, you can compare any nested models, different in means or variances or both. And I'm looking for the order. It's always the model with fewer parameters minus the one with more. So some of these are in the wrong order. The one with more is going to be in front of the one with fewer, and that's what makes them wrong. So I'm looking to see you generalize these rules and apply them to these specific instances in this. This is not due for another 10 days or something, though. So, all right. And that's the rest of chapter 3. Does that help, Teresa? Okay. Even without the suckers? All right. Questions on that, or any that you want to hear again or more about? No? Okay, then I'm going to leave you with a bit of trivia. So here's my stick for the very first time. This is a picture of me from 2004, standing in a classroom in Göteborg, Sweden, teaching for my very first time ever teaching this class, Longitudinal. And I am teaching it in SPSS because that's what they have in Europe. Note that my hair is a little longer, but otherwise I've got my stick, and I enjoyed the stick. That was where I first got into the stick. And so then, as part of that same trip, we went over to Switzerland, and I gave a talk in Zurich. And there's the giant stick. Seriously, this thing weighed a ton. I'm like, take the picture. So that was very fun. On that trip, I got a chance to go hiking in the Swiss Alps. And here's a picture of me with our host, Mike Martin, at the beginning of the hike. Note that I am wearing a Hilltop Hustle 2003 souvenir t-shirt from back in the day. It's probably still in my closet somewhere. Note that we've been hiking for a few minutes and my sleeves are rolled up. I'm getting a little warm. Cut to about an hour later, and this is me in the fog with my jacket on, freezing my ass off. In the middle of the Swiss Alps, though, so how cool is that? And then last but not least, I wanted to show you a picture of the people that I always end up talking about. This is Daddy and Huey. Mabel had us come in to do a little photo shoot, and we got some cute photos out of that, but this is the little stinker that won't go to sleep anymore. Fortunately, Daddy and I now trade off. Whoever's not teaching the next day gets to get up with them. So I get to sleep every other day, which actually means I get to hear him screaming on the monitor but not do anything about it. So I get to wake up and lay there. But he's 2.5 and he is opinionated as hell, but it's a good time. So we're done. I don't want to start anything with 7 minutes to go. You can start reading chapter 4. I will warn you, it nearly killed me to write it. It's like the boringest thing in the world. But it's one of those topics that you have to go through to get to the stuff you care about. So I will give you that. This is the only homework assignment you'll have using those models, and so I'm looking to just give you the set of options besides the everything gets to be at once and 2-pile models. So we will see those next week. Office hours start now if you'd like to hang out and chat with me. And I still have suckers left.